Welcome to this tutorial on complex sounds. We have already discussed the simplest sound, a sine wave, created by a source vibrating in simple harmonic motion. But all natural sources vibrate at multiple frequencies simultaneously. Each individual vibration or sine wave is known as a harmonic. These harmonics interfere and interact with each other in a complex process of phase summing and cancelling to produce an overall complex sound wave that contains all of the individual harmonic vibrations. Sounds created in nature are very complex. We can use an oscillator to create less complex waves, but even relatively simple waves, such as a square wave, are many times more complex than a sine wave. One of the wonders of nature is the human ear's ability to deconstruct a complex sound wave, hear all the individual harmonics, and identify the sound source. So when we listen to a single sound, such as a snare drum, the brain recognizes it from its unique combination of harmonics. But the brain can also decode all of the individual harmonics in all of the individual sounds that comprise a completed mix, thus allowing us to identify the individual instruments. It's truly amazing that so much information can be carried by a single pattern of changing air pressure energy and the harmonic content deconstructed by the brain. To illustrate how harmonics combine to create a complex wave, it is practical to use the example of a square wave. This diagram shows some of the individual harmonics required to create a square wave. You actually need at least 20 harmonics to approach a squarish shape. Because the harmonics are simple integer multiples of the fundamental harmonic frequency, that is 3 times, 5 times, etc., it is simple to calculate how they combine to create an overall wave or timbre. You simply move along the timeline, adding together the positive, compression, and negative rarefaction values of the waves at regular intervals. In a complex sound, the harmonic with the highest amplitude, the loudest, and the lowest frequency, the bassiest, is known as the fundamental. It is also known as the first harmonic. Additional harmonics, each with a progressively lower amplitude and higher frequency, will be named the second, third, fourth, etc. harmonics. Higher harmonics are often referred to as overtones by musicians. Oscillators apart, every natural sound source produces a unique pattern of vibration. The unique relationship of its fundamental and subsequent harmonics create the unique character of the sound, which is known as its timbre. Natural sound sources produce enormously complex timbres made from many hundreds or thousands of individual harmonics. No matter how many harmonics a sound comprises, they are all represented by one single pattern of compression and rarefaction, a single wave of energy. Sounds which have a definite fixed pitch are distinguished by having a repetitive waveform. So, for example, a single sine wave vibrating at a constant frequency will have pitch. Although complex sound waves are made from multiple harmonics vibrating at many differing frequencies, they can have an overall frequency or pitch. This is true of musical instruments and singers, provided they can sing in tune. This overall frequency is usually determined by the loudest harmonic, which is nearly always the fundamental. The script for this tutorial, with accompanying images, can be found at our website, projectstudiohandbook.com. And finally, don't forget to join our mailing list to receive notification of new videos, blog posts, and subscriber-only extras. And also, subscribe at our YouTube channel and social media pages. Thanks very much for watching.